In this video, we're going to be looking at 1.4 polynomial functions and rates of change. So polynomial functions are functions really of the form that we see down here, where we have all these different terms. We're showing it in this more analytical style. The a's, the x's, and the n's can be a little bit confusing to really understand. But if we understand that it's something like this cubic down here, or quadratic, or power of 4, or something like that, that is a polynomial, where poly means many, many monomials. So polynomial, it's the many different terms with powers. And within our polynomials, we have our degrees, which is going to be the highest power of our problem, the highest exponent, and we use that letter n to represent that. We then have our leading term, which is going to be the term with that highest power. And then the leading coefficient is going to be the coefficient of that term. So all of this information is pulled from that first term. So looking at problem number 1, we want to find our degree, leading term, and leading coefficient. So we see our leading term right there. That is our leading term, that 5x cubed. 5x cubed is our leading term because it has the highest power. So what is our degree? Well, our degree would be, again, that highest power. So that right there is our degree. Go ahead and highlight that. So our degree is that power right there. That is our degree. And then our leading coefficient is the number in front. So in this case would be 5. So degree of 3, leading coefficient of 5. And we'll be using that later on. And I'll be using the letters L, C to represent leading coefficient, so I don't have to write that out. It's important to note that a constant function like f of x equals 3 is also a polynomial function of degree 0, because if we think about it, that would be f of x equals 3 times x to the 0 power. But what is anything to the 0 power? Well, just 1, so that is equal to 3. So whenever you just have a plain old number, that is also a polynomial of degree 0. Another note, a function has at most n real zeros, which means it can cross the x-axis at most n times. Now remember, what does that n represent? Well, the n represents our degree, so that is the degree of the function. So if we go back up to this problem right here where we had a degree of 3, that means that this function f of x has at least or at most 3 zeros, no more than 3. It can have less than 3, but it can have no more than 3. Now, being polynomials, we could have in the cubic function, as we see in these graphs, we could have 1, 2, or 3 zeros. So where we hit the x-axis that many number of times, whatever my degree is, we hit it that many times. We could hit it just twice, or we bounce off on one of them. We're going to be calling that a multiplicity of 2 in another section. But that would give us 2 zeros. And then where we have our bump underneath, it never even crosses at that point, but crosses 1 time elsewhere, and that would be 1 real 0. So we could have 3, 2, or 1 real zeros when we have a cubic. If we have a quadratic, we've seen that before, we can have 2, 1, or 0 real zeros. Sometimes a polynomial will not be written in standard form, and you must look at the variable with the largest exponent to find the leading term. So looking at this problem here, same as problem number 1, we want to find our degree, leading term, and leading coefficient. Well, let's find that leading term. Leading term should have the highest power. So even though it's not first, here is our leading term, negative 2x to the 6th, where our degree is 6 and our leading coefficient is -2. Okay, extrema, a little bit of review. We looked at these in a previous lesson where we have our global or absolute extrema, absolute max and absolute min. And then we have our relative max and relative min. Now remember, endpoints can also be local extrema. That is okay. So we're going to be using our information on that on this problem here. We want to go ahead and find the extrema and where they occur. If none exists, cross it off and write none. So first off, we see our absolute min happening right down here. And it is an absolute minimum value of -2 when x equals 6, -6. So when we are looking for min or max values, we look at y values. So whatever our y value of the point is, that is going to be the min or max value. When we want to look for location, so min or max locations, we go ahead and look at the x values. The x value tells us where it happens, or when it happens, and the y value tells us how much it is. So y values to give us the actual value, the actual max or min value, and the x value to tell us where it occurs. All right, so that's our absolute min at x equals 6 with the max absolute min value of -2. Our absolute max. All right, so as we travel along our graph, we're traveling along our graph, do we ever reach a highest point? And the answer to that is no, we do not reach a high point. This graph, as we can see, is increasing forever, increasing without bound. It is actually going to infinity. And infinity is not a number. I can't cap it off. I can't say, oh, my max value is infinity, because infinity is not a number. I can't do that. Remember, a max value has to be a y value, and infinity really isn't a number. Infinity is a concept that we are getting extremely large. We just keep on getting bigger and bigger and bigger. So whenever we are increasing or decreasing without bound, there is no absolute max or min. So they told us if none exist, cross it off and write none. So there is none there. All right, relative minimums. Let's go ahead and find those. So relative minimums, looks like I have one here and one here. They don't ask what the values are, they ask where they are, those x values. So that will be at x equals -3 and x equals 2. All right, and then let's see, our relative maxes, looks like I have one here and one here. So that is going to be at -4 and at 1. -4 and 1. All right, let's go ahead and move on. So next thing that we're going to talk about is when we have two zeros, we have at least one extrema in between them. And that is because however I graph this function, if I'm going to be coming up to my x value, well, I have to eventually drop back down to this one. So I'm going to have that extrema, either a max or a min, in this case a min. But if I am coming down to this point, I have to eventually go back up. And I have a minimum. What if I come down but then bounce off? Well, I still would have to come down. Even if I bounce off, I have to come back down. It gives me a maximum. So no matter how I was to draw a function, I have one going like this, And I still have some maximums or minimums in between. It guarantees that I have at least one. I could have, like I just drew, I could have more than one. I could be going up and down a whole lot and have lots of maximums or minimums, but I know I have at least one. So, using that idea, thinking about this function here, in this problem it asks, let f be a polynomial function with values given in the table below. Based on the data, are there any guaranteed extrema? If so, state the interval where they occur. Well, using the idea that we just saw, let's go ahead and identify any zeros. So I see a 0 here and a 0 here. Remember, a 0 is when our f of x is equal to 0. And there we have it. So if I have two zeros there, that means somewhere in between them is a max or a min. So we can go ahead and say that. So there is an extrema in the interval -2 to 4 since x equals -2 and 4 are zeros. Is that the only extrema guaranteed by this data? To help us see if there's any more, let's go ahead and plot our points and see what we have. So -2, 0, 0, 5, 4, 0, 7, -1, and 12, 6. So let's go ahead and sketch our graph. So I'm coming up through the 0, I hit this point, and I eventually have to come back down through that point. I have to go through this one, and at some point come back up here to this point up here. Let's see. All right, I like that better. Okay, so we saw between -2 and 4, we saw that there was an extremum. We have one right here. We have a maximum. We know there has to be a maximum there. There is that extrema because we had those zeros. Between those zeros had to occur an extrema. Remember, it doesn't have to be the only one. I could be coming up and doing a whole bunch of extremas within that interval, but I know it is at least one there. However, looking at our graph, do we have another extrema with the points that we have? And we do. In this area, we also have an extrema. It might not necessarily be this point. That's kind of how my graph is drawn. But it could be a different point. Say I drew this slightly differently. So I had a point here. Say I came down and then started coming back up like this. Say that was my graph. Well, now my point's over here. So it's not guaranteed that this blue point is our extrema, but we can definitely see that we have an extrema somewhere in this area. And why is that? Well, we weren't given a 0. There's not another number here that was a 0, but what are we given? We are given that at 7 we are at -1, right here at -1, and then at 12 we're at +6 right here. Well, if I'm going from a negative to a positive, what do I have to cross on the way going from the negative to the positives? I have to cross the x-axis someplace. So because I am going from a negative to a positive, there has to be a 0 in between. We don't know what it is, but there has to be a 0 here because I am going from a negative to a positive. Well, if I have another 0, well, then that guarantees that minimum that I have. So we have another extrema. So let's go ahead and state some of that. Since f of 7 equal to -1 is negative, and f of 12 equal to 6 is positive, there is another 0 somewhere between x equals 7 and x equals 12. So our conclusion, there exists another extrema on the interval, or extrema in the interval somewhere between, so it's somewhere in this area, so we can say somewhere between 4 and 12. Somewhere between 4 and 12. I can't guarantee between 4 and 7, but I can guarantee somewhere between 4 and 12. Because somewhere between 7 and 12 is another 0. Now, it might be all the way at like 11.9. I don't know where that 0 is, but I know it's somewhere in there. So there exists another extrema in this interval, 4 to 12, since x equals 4 is a 0, and there is a 0 in the interval 7 to 12. All right, so we are guaranteed 2 extrema. And again, could we have more? Of course we could have more. We could have lots of extrema going on in here. But from the data given, we can guarantee 2. Not 1, but 2. Possibly 3. I don't know. It's possible. We don't know. We don't have enough information. All right? But we do have enough to guarantee 2 extrema. All right, moving on. Let's go ahead and look at this one. This will be our last thing for today. And this is talking about the even degree of polynomials and absolute extrema. So if the polynomial has an even degree, and this is very important, it needs to be an even degree, 2, 4, 6, 8, 12, 96, whatever it is. If it is an even degree, then there is an absolute maximum or absolute min. We can say that it exists. It exists. There is one. We can guarantee that there is an absolute max or an absolute min. Not both, but one or the other, if we have an even degree. So why is this? Well, let's go ahead and think about parabolas. So if I have y equals ax squared plus bx plus c, what is the shape of a parabola? Well, we know it's either this or this. Those are parabolas. Well, if you look at the parabola, I am guaranteed a max, or this is a min, and this is a max. And those are absolute. Absolute max. Absolute minimums. And how can we tell if it's an absolute max or absolute min? Well, if our graph is opening up, it's going to be an absolute min. If we're opening down, then that is an absolute max. And the nice thing is that this holds true whenever our degree is even. If our degree is even, this will happen. And how do we know if we're opening up or opening down? Well, that's our leading coefficient, that a term, our leading coefficient is, and this one is greater than 0. So if our leading coefficient is positive, then we're opening up and we have an absolute minimum. if our leading coefficient, is negative, then we're opening down and we have an absolute maximum. So that's what we're saying here. A positive leading coefficient means you will have an absolute. Well, remember, positive means that we will be concave up. So concave up, opening up. Well, if that's the case, we have an absolute minimum. And if we have a negative leading coefficient, as we just discussed, that would be concave down, and that would give us an absolute maximum. It's pretty nice. So let's go ahead and look at problem number 5. We have A, B, C, and D. We want to figure out, do they have an absolute max, an absolute min, or neither, and why? Well, the first one we look at, remember, we want to find our leading term. Here's our leading term. And looking at that information, we can say that we are an even and positive, so that would be opening up. So that gives us an absolute minimum because our leading coefficient, which is 3, is positive, it's greater than 0, and our degree, which is 4, is even. Looking at our next one, we find our leading term. Here it is. This is our leading term. And that is an even degree and negative, so that would be opening down. So that would give us an absolute maximum. So absolute max. Again, why? Because our degree, which is 6, is even, and our leading coefficient, which is -1, is less than 0, or is negative. All right, looking at our last one, we have our leading term right here. Do we have an absolute max, absolute min, or neither? And in this case, it would be neither. Why? Well, our degree. And this is because, or since, our degree is odd. And that ends it right there. I don't even have to look at the leading coefficient this time for this type of problem, because once it's odd, I know I do not have a max or min. All right, and that pretty much ends it. This information down here on concavity and points of inflection is review, so you can go ahead and look at that. But that ends this video. Got a lot of more information and ways that we can look at polynomial functions. Thank you for watching and have a great day.